Hello there, children. Today, we are going to work with solving linear systems by graphing. This educational experience is brought to you by your legend of linear, Math Wizard Faust. Me. So, let's get started. So, in graphing systems of equations, we could have three situations. Situation 1 is where we have two lines that intersect once. So I have two lines and they happen to cross at some point. This point right here will be the solution. What that means is that is the point on my graph which will satisfy both lines, that will make both of them happy, that will work in both equations and give me a true statement. So that will be one solution. The other situation I could have is I graph lines and they are in fact the same line. One is just a scalar multiple of the other, which means just multiply by a number, so they end up graphing to the same thing. What this means is there are literally two lines stacked on top of each other here. That means there are infinitely many solutions, because why is that? If I poke something through line 1, line 2 is sitting directly on top of it, and we'll go through that one as well. So any point I pick on this line, since there are actually two lines there, it's going to work for both of them. So I have one solution, I have infinitely many solutions, and then lines are parallel to one another, which means I have no solution. What that means is I have two lines that never cross. So there is never an intersection, which means for me that I never have a point on one line, an x value giving me a y value, that will work on the other line. Whereas in this one, if I pick that black dot right there, it satisfies this line, meaning satisfies when I pick an x, I get a y value, which will be the same thing as this line. The problem over here, if I pick an x value, I will achieve two different y values. Over here, I pick an x value, and since it's one line, everything on that line all the way down it an infinite number of times is the same thing. So let's move on and do some examples. So let's look at this example here. Now I have two equations. Y equals 2x plus 3 and 2y minus 4x equals 6. So I've got an option here. Option 1 is you just graph the lines as they presently sit. So that means I graph 2x plus 3. I'm going to graph that in, let's go with red. Why not? So I graph this line. My y-intercept is 3. Boom. My slope is 2. So I rise 2, run to the right 1, or I go down 2 to the left 1, because those two negative directions will make a positive slope still. And then I graph my line. Sound effects optional. Now, that's not bad, because that's in y equals mx plus b. This other line, you have choices. You can graph it in standard form if you like, by simply covering up the y to find the x-intercept, and covering up the x to find the y-intercept. Some people are more comfortable with turning it into y equals mx plus b. So we'll do that here just to show you what it looks like. So this particular graph, I'm going to solve for y, which means I'm going to add 4x to both sides. Is y by itself? No. So I'm going to divide everything by 2. And I do mean everything, because sharing is caring. Thank you, imaginary voice in my head. So we divide everything by 2. So when I do that, and I'll graph this line in purple here, I get 4 divided by 2 is 2. 6 divided by 2 is 3. So I graph my y-intercept of 3, and then I go up 2, over to the right 1, or I go down 2 to the left 1. Huh. What just happened? Oh, snap! These two are in fact the same line, and how can you tell? Look at the equations. They're the same. So that means I'm going to do a dotted line. This is really solid, folks. This is really a solid line. Again, it's solid, but I just want to show you here that that works. So what is this? Well, that would be infinitely many solutions because the lines are literally the same thing. So what a lot of people will do is they will use this infinity symbol. It's like an 8 that fell over. They will go infinitely many solutions. They will write out infinitely. Alright, let's move on. Alright, so let's look here. Let's graph these two lines. One is in y equals mx plus b. I'll tackle that one first. I will graph this one in orange. Alright, so I look here. And alright, I graph the y-intercept of 2. And then I use my slope of -1 there to go down 1 to the right 1. Or up and to the left. Now, this other coordinate, how am I going to graph that? Well, two ways you can graph that. I'm going to graph this one using my standard form this time and graph it in this lovely color right here because I solved the last one for y equals mx plus b. So how do I do that? To find the x-intercept, remember, you set y equal to 0, which means I get 2x equals 6, which means x equals 3. That's my x-intercept, the coordinate 3, 0. Boom. I then, to find my y-intercept, I let x equals 0, and I get 2y equals 6, which means y equals 3, which is the point 0, 3. Boom. I then connect my dots and, what happened here? They don't touch, which means I have no solution, which if you think about it kind of makes sense. Because if I were to actually solve the bottom equation here for y, I would subtract 2x, divide everything by 2, and get negative x plus 3. Look at these two equations. These two have the same slope, but different y-intercepts. Same slope and different y-intercepts means they are in fact parallel, which is why they will never touch. Alright, let's move on. So, let's graph these two. Oh, phew! They luckily put them in slope-intercept form for me. How nice. So I'll graph this first one in blue. Plot my point of 2. Then go down 3 to the right 1 for a negative slope, or up, which is positive, left, which is negative. And then I just connect my dots. Send effects optional. The other one I'm going to graph, let's go red again. So I have this point. Alright, I'm going to graph the y-intercept of 3. And then I use my slope of 4, which means I go up 4 to the right 1. Or I go down 4 to the left 1. And I connect my dots. Again, sound effects optional. Alright, so how many solutions do I have? Well, they cross once. So I have one solution. But this brings me to a problem. What if I ask you what that solution actually was? And you go, well, it's here. Cool, that's exactly where it is. It's the intersection of the graphs. But what if I asked you for an x equals and a y equals here? This is where the graphing method is a little weak, because you can tell the intersection, but unless this intersection is a whole number, at like one of these crosshairs, for instance, it's really hard to tell the exact value, which means we'll have to solve it algebraically later. You can tell there's one solution graphically and do it very quickly. And infinitely many and no solutions are very easy to see. But if I asked you for the exact value here, and that is in fact not on these crosshairs or integers, you're going to have problems. But let's move on to what else we can do here. So, Is the following a solution to the system of equations? In order for it to be a solution, it must work in both equations. So I give you an equation here. I give you the point 3, 1. And I ask, does it work in both of these problems? Now, think about this logically. It's like if you and your significant other were going out to eat somewhere and you select a place, like Red Lobster or Chili's. You must check with both parties involved to make sure that that's somewhere okay. If you have a fish allergy, you're not going to go to Red Lobster. And if you are a vegetarian, you're not going to take somebody to an all-you-can-eat steak restaurant. While tasty, might offend the other person. So let's check these. So let's check in this one. That means I put y being 1 and the x value of 3 into the problem. I get negative 3 plus 4 equals 1. That means 1 equals 1. All right, and I'm done. No. It worked in one. Does it necessarily work in the other one? I don't know. Let's find out. So I put x being 3 and y being 1 in here. I get 15 minus 3 equals negative 15. I get 12 equals negative 15. Wait, hold up. Hey, no it doesn't. That's wrong. That's sad. So no, this is not a solution, because even though it worked in one of them, it does not work in the other one. So it is not a solution. I picked a restaurant. One person's okay with it. The other one's really not in the mood for that. So no. Now, just so we're clear, if you had attempted to put the x being 3, y equaling 1 into the bottom equation, and you found that failed, you don't need to go check the other one. Once it fails once, you're done. All right, moving on. Okay, so now, check the following point. Is the following point a solution to this system of equations? So I'll take the first one in orange. All right. That means I put y being 4, and I put x being 1 in there. That's 2 plus 2. That is 4 equals 4. There we go. That's a good solution so far. But it's not the only game in town. So I've got to go check the other one now. So I'm hopeful. I found a place that one person's okay with. Is the other person going to be okay with this now? Well, let's give it a whirl and find out. As I check this, I get 4 minus 24 equals negative 20. Woo, look at that. Golly gee willikers. Negative 20 equals negative 20. That also is true. So I put it into the top one, I substitute it in the bottom one, and it works. So yes, in fact, it is a solution. What does this mean graphically? This means graphically that if I were to graph these two graphs on the same coordinate axes, their intersection point would be 1, 4, which, as long as you're good at graphing, you will clearly see that because they are integer solutions. So the graphing method would be fine to solve this. You now have enough knowledge to go forth and take on the world, and this lesson, go henceforth and do.